Every time you slide that nozzle into your tank, there's a number on that pump that is not telling you the whole truth. Not because the meter is broken, because the engine burning that fuel was never designed to use all of it. The average gasoline engine in your driveway converts less than 72% of the fuel it draws in into actual motion. The rest exits as unburned hydrocarbons, heat loss, and wasted combustion, publicly documented in EPA combustion studies from 1978 to 1983. What is buried is proof that a specific additive compound, costing under $4 at any hardware store, can push that efficiency from 70% to over 93%. That gap is not a tweak. It's the difference between filling your tank twice a week and filling it once every 11 days. And the people who have been doing exactly that, quietly for over 4 decades, are not engineers. They are farmers in Lancaster County, Pennsylvania, running equipment that should have died in 1987, still recording mileage that would embarrass a modern hybrid. That story does not begin in Pennsylvania. It begins in Winnipeg, Manitoba, in the winter of 1935, with a machinist named Roland Whitfield who was not trying to save fuel. He was trying to heat it. Whitfield had noticed that carburetor performance in Canadian winters degraded badly because gasoline at low temperatures resists clean atomization. His solution was counterintuitive. He introduced a low molecular weight solvent into the fuel mixture ahead of the carburetor throat. Not to thin the fuel, but to lower its surface tension at the molecular level, allowing it to break into finer particles before ignition. His bench tests, documented in a mechanical trade circular published in February 1936, showed combustion efficiency improvements between 18 and 31%. The circular was read by working mechanics across the upper Midwest and never picked up by any major automotive journal. The primary advertisers in those journals were petroleum distributors with no commercial interest in efficiency gains that reduced volume. That is the first time this knowledge was buried, filed and forgotten, the way inconvenient data tends to disappear when it threatens a revenue model built on consumption. The principle did not disappear. It migrated into the notebooks of rural mechanics who read trade circulars and into communities that maintained old equipment by necessity rather than preference. By the late 1950s, variations of the compound were in documented use across farming communities in Ohio, Indiana, and Pennsylvania. The formulation had evolved through practical trial and converged independently among different communities on a surprisingly consistent ratio: 1 fluid ounce of a methanol-adjacent solvent per 10 gallons of fuel. Not 9, not 12, 10. The consistency of that number across communities with no documented contact is itself a form of evidence. Physics does not care about regional variation. When independent observations converge on the same measurement, that measurement is usually correct. What those rural mechanics were observing is something combustion engineers now understand formally but rarely publicize commercially. Gasoline is not a uniform substance. It is a blend of hydrocarbon chains of varying molecular weight, and the heavier chains, the ones that resist vaporization, are precisely the ones most likely to exit the combustion chamber unburned. A light alcohol solvent introduced at the correct ratio acts as a co-vaporizer. It does not replace the fuel. It lowers the energy barrier required for heavy chain molecules to transition from liquid to vapor state inside the intake manifold. More vapor means a more uniform fuel charge, which means more complete combustion, which means more energy extracted per gallon. What is complicated is why a century of automotive engineering has never formally integrated this into standard consumer fuel chemistry. The answer, once you understand that a 15% efficiency improvement represents approximately $80 billion per year in reduced gasoline sales in the United States alone, becomes considerably less complicated. That figure does not include downstream effects on service intervals, component longevity, or catalytic converter replacements, all of which improve significantly when combustion efficiency rises and carbon accumulation slows. Here at Secret and Solutions, that buried arithmetic is exactly the territory worth mapping carefully. An engine running at 93% combustion efficiency instead of 70% produces less unburned carbon per cycle, which means slower deposit formation on intake valves, injector tips, and piston crowns. Slower deposits mean oxygen sensors that read accurately for longer, which means ignition timing that stays calibrated to factory specification rather than drifting to compensate for false sensor data. Mechanics who have serviced vehicles maintained under this regimen consistently report compression readings within factory tolerance at mileage figures where standard maintained engines of the same year show measurable cylinder wear. That is not anecdote. It is a pattern across documented observations, spanning multiple decades. The compound requires no mechanical modification, no permit, no specialized equipment. The active ingredient is a methanol-based fuel line treatment sold commercially as a winter fuel system conditioner. The yellow-labeled variant available at hardware and farm supply stores contains the correct base concentration. The dose is 1 fluid ounce per 10 gallons introduced into the tank before fueling, so the incoming fuel mixes uniformly rather than settling beneath it. That sequence matters. What farming communities in Holmes County, Ohio, and Lancaster County, Pennsylvania discovered, and what a 1979 Penn State agricultural extension study quietly confirmed before the document was archived without publication, is that a secondary co-solvent amplifies the base effect substantially. 1/4 ounce of xylene per 10 gallons combined with the methanol treatment addresses the heavier hydrocarbon fractions that alcohol alone cannot reach. Xylene is available at any paint supply or hardware store for approximately $8 per quart and treats an enormous volume at that concentration. The combined cost works out to roughly 11 cents per fill-up on a standard 26-gallon tank. The Penn State study, funded by the USDA and tested across International Harvester and John Deere equipment operated by Lancaster County communities between 1976 and 1978, documented improvements ranging from 84 to 109%. The paper was archived in 1980 and never submitted to a peer-reviewed journal. A footnote reference appears in a 1993 Ohio State graduate thesis located in person in a Columbus Research Library in a document that has never been digitized. The vehicles that respond most dramatically are not the newest ones. Pre-1996 engines, built before OBD2, monitoring standardized emissions compensation, have no onboard mechanism to counteract the efficiency gain by retarding timing or enriching the mixture in response to sensor data. The engine simply runs cleaner and returns the improvement directly to the odometer. Older carbureted engines show the sharpest gains, which is precisely why the communities that kept old machines running also kept this chemistry alive, while mainstream automotive culture forgot it entirely. If you maintain a vehicle built before 2000, the additive cost on your current driving pattern is likely under $20 for a full year of use. The first 3 tanks typically show progressive improvement as carbon deposits dissolve and sensor accuracy recovers. By the 5th tank, the gain stabilizes and it does not degrade. 1 ounce of the methanol treatment plus 1/4 ounce of xylene per 10 gallons every fill-up is the complete regimen. Write your mileage before the first treated tank and again after the 3rd. That comparison will be the most persuasive document you produce this year. What year and make is the vehicle you're planning to test this on, and what is the current odometer reading? Leave that in the comments below. The responses will form the data foundation of a follow-up video that Secret and Solutions is building around real-world mileage logs from viewers who actually ran the numbers. If your vehicle predates 1998, your data is especially valuable. That is the range where gains are sharpest and documentation thinnest. Subscribe to see those results because the next video in this series documents something older, quieter, and more deliberately buried. A thermal management modification used by industrial foundries in the 1940s that extended engine service life by a margin the modern parts industry has spent 70 years hoping you would never calculate.